Oh, that was nice. Do it again.
Riding on a big white butterfly, I turn my back away towards the sky. Close my eyes to look for something, so myself is really nothing. Then I realized my butterfly wasn't really up there with me. We all make mistakes, forgive me. Would you like to ride my butterfly? Riding on a long blue paper plane, getting seasick, sorry once again. Landing strip is getting near, hope the fog lifts, make it clear. Then I realized my paper plane wasn't really up there with me. We all make mistakes, forgive me. Would you like to ride my paper plane? Riding in a 3 grand Deutsche car, A to B is often very far. Home is near but such a long way. Legs and heads all feel the wrong way. Then I realized my Deutsche car is only there to get me somewhere. Even so, I really do care. Would you like to ride my Deutsche car? Would you like to ride my paper plane? Would you like to ride my paper plane? Would you like to ride my paper plane? Would you like to ride my paper plane?
I just want to finish up with what we were doing on Monday, where we're going to organize all of our books into an author, which is a person, which is going to map to a list of books. You could also do a set of books instead if you want, if you don't care about the ordering. But we'll go ahead and go with the list because that's already what we wrote. We created a map here to do this already. And what we wanted to do is we'll outline this, that for each book, you find the author's key, or you've got the author that wrote that book. You want to get the list of things that they, or you want to get the list in this map here of the books that you've already seen and added. And if the list exists, then you just add the book. If it doesn't exist, you need to create it and add the book, right? So let's go ahead and start replacing each one of these lines with some actual code. All right. So for book B in this collection here, right? All right. For each book, we're going to find the author that wrote it, and that's simply just part of the object, right? Person author is equal to b.getAuthor. Right? Because I already invested the time up front to design these objects and have a bunch of getters and toString methods and stuff like that, that investment is now paying off now that I'm looking at now that I'm using it, right? So again, it's a bottom-up approach. You create the objects, you design the objects that you're eventually going to need. Maybe you didn't design them perfect. That means that you're just going to have to go back and reiterate on them. But at least you have those building blocks to start building up on this. Now let's find the author's list. So that's going to be a list of books. Right? Author's books, right, is equal to author to book. And we've got this key here, which is our author. .get author. Now, if the list exists, we just add the book. If it doesn't exist, then we need to create it. So let me bring that up and do that first. How do we know if it doesn't exist in the map? What value will this have when I get it, a key that doesn't exist? Null, right? So if author book is equal to null, all lowercase there, then we need to create it. So author's books is equal to new array list. It's just empty. It's just an empty list. And also, I'm going to put it back into the map so to ensure that it's in the map. So author to books dot put, what would be author is going to map to the author's books. Right. Otherwise, this is not the first time we've seen it. It already exists. And if it already exists, then that means that this has been initialized, and we just simply add it. Right? Not some Murakami book, but B. Right. Why didn't I add it here? I could have, but then that would mean I would have to have an else statement here. And I would end up doing the same thing in both if and else blocks. So I'm not going to do that. All right, let's see if it worked. All right, now if I just print this out, it's not going to look very nice. So let's make sure that it looks nice and pretty. That for each person who is an author in author to books key set, right? In other words, I'm going to iterate over all the keys. I'm going to print out the author. System.out system.out.println author. And remember, because I've already invested the time to do a toString method, we're good on that. And then for each book, for book B in the collection, there we go, authors to books.get author. Right? I'm going to get all of their books and I'm going to print those out. System.out println. And what I'm going to do is I'm going to put a tab in front of it so that it's indented. So you'll have an author and then a list of their books all indented under that author. Right? At least that's the ideal. Let me run this and see if it actually works, though. Kinda. Right? Actually, are we running the right one? Person? Oh, whoa. We already did this? We already did the toString and hash code? Or the hash code and equals? I intended not to do that, so let me go ahead and get rid of that for now, and we'll come back to it. Right? All right, so I think we did it last time, and I said we're going to need it. That's because it was me looking ahead. When I didn't want to look ahead, I wanted to find this error right here. Right? All right, so let's take a look at Janelle Monáe, or memory librarian. Robert Heinlein, The Moon is a Harsh Mistress, etc. Now we've got Frank L. Baum. He actually wrote, in this collection, I've got 5 Oz books there, but I only see 1. Right? If you keep going down, though, you'll find another Frank L. Baum with Ozma of Oz, another one. And if you keep going, you'll find the other 3. The problem here is that it was treating all of those Frank L. Baums, there are 5 Frank L. Baums, it was treating them as separate because it had no way of determining that that Frank L. Baum is the same as that Frank L. Baum over there. And that's why we generated this code. So that if you've got 2 objects, are they equal? They're equal if their first names are equal and their last names are equal. Right? And so that when it saw that Frank L. Baum, oh, that's the same Frank L. Baum as over there. I will consolidate their books into one list. And when I've got that restored, it will actually output the correct thing. Where are you? There we go. There's Frank L. Baum with all 5 of his Oz books right there. At least they're in the collection. There are dozens of them. Right? Or a dozen or a dozen and a half or something. Right? All right, so we've got all their books. There's the 2 Terry Pratchett books. He's got several dozen that are not in this. And then there's my Haruki Murakami books that we all started out with. We wanted to find a Haruki Murakami book. We used binary search. We wanted to find them all. Well, okay, let's expand that out. I want to find all books by all authors. And a map turns out to be a perfect way of doing that. Okay? All right. Any questions? Yeah, go ahead.
What's the hash code?
Good. So the hash code is necessary because we're using a hash map. Okay. So let me come back over here to the person, right, and let's look at it. All it's doing is taking the state of this object, the first name and the last name, and it's converting it into an integer. Right? That integer doesn't have to be unique. I could have author A and author B, and they hash to the same value, 1, 2, 3, 4. Right? If they do, then that hash map, what it'll do is say, oh, they hash to the same thing, but are they the same thing? That's when it goes to the equals and says, yes, they are the same thing because they have the same hash and they have the same first name and the same last name. But if they are different, author Joe and author Beth, right? They hash to the same 1, 2, 3, but then the equals will say, no, they're not the same thing. And so the hash map knows, okay, then I need to store them in different locations. Right? And the hash code is used in all hash-based data structures. We've seen that with hash maps. You can also have sets of person, authors is equal to new hash set, right? And if you did not have that hash method, then you might not get the results that you want. Frank L. Baum and Frank L. Baum, they're two different people, even though conceptually they're the same, right? The default implementations, we can look at that actually. The default implementations will always give you correct code, but not necessarily the code that you want. So here, object, right? We can look at the default, okay, never mind, it's native. That means that it's built into whatever C library is under the hood, right? But generally, it will be as far as reasonably practical. It's defined returns distinct integers for distinct objects. So there's the key words there. As far as it is reasonably practical, not always, right? And returns a hash code for the object. So, but usually it's based on the memory location. Right? And that's because that's all it has, right? This object, what is it? I don't know. It's in memory though, so that's all I can use. Likewise, the equals should be reflecting here. Yeah, equals equals. So what does it do? It looks at the memory location, and those two objects are the same if they're stored in the same memory address. Right? Okay. But yeah, we'll talk about hashing later on a little bit more when we get into more object-oriented programming. Right? But otherwise, that's all I wanted to do as far as that demo was concerned. So a day and 10 minutes is all it took us to go through that last week or two of CS1. Right? Okay. That'll be posted if you want. Otherwise, if you want to answer other questions, right, about this, then what else could you answer? What do we have in a book? I want to find one with a particular ISBN. That's not very interesting. You could do the average rating, right? Mean, median, whatever, right? But none of that's really all that interesting. What is interesting is physics, right? So this is going to be a little demonstration. Right? We're going to start out with basic Java, but this goes all the way back to, I don't know, maybe the first 4 weeks of a CS1 course. We're going to do this exercise because what we've known up till this part, up until this point, is what's called imperative programming, structured imperative programming. That when you program something, you write a line. You're telling the computer to do something. Declare an integer and set it equal to 42. Right? You add 45 to the integer A, it's stored in A, and then put it back into the variable B. Right? Print out the result. Those 3 lines are imperative. I'm telling the computer what to do. Right? We know imperative sentences from grammar. Right? Interrogative would be a question. Imperative would be a command. And so that's why we call it imperative programming. Right? And that's what we know up to this point, even though we've used Java, which is an object-oriented programming language, even though we've used Python, which is a functional programming language technically, and also has classes, we've only touched the surface of object-oriented programming. And I'm going to use this program as a demonstration for how it is vastly different conceptually from structured programming or imperative programming here. So let's understand the physics though, right? Everybody knows radioactive isotopes. Don't eat them, right? They are radioactive and give off radiation. Alpha decay, beta decay, gamma decay, or the worst is neutron decay, right? And we've got strontium-90 here, which is a byproduct of nuclear fission. So a nuclear explosion would leave a lot of strontium-90 in the environment. And it has a half-life of 28.9 years, or thereabouts. I think it's actually 28.89 or something, whatever. So in other words, if we start out with 10 kilograms of strontium-90, then 28.9 years later, we would only have 5 kilograms of strontium-90. Now, it doesn't just evaporate. It decays into uridium-90 and zirconium-90, which are also radioactive isotopes. Those will decay into something else. Those will decay into something else until it reaches a stable non-isotope that's not radioactive and will not change unless you blow it up again within a nuclear explosion, right? So what we're going to do is we're going to read in some data here. An atomic number, that's, is it 90? Right? 90 is the atomic number there? I think, yeah, that's the isotope weight, isn't it? What is strontium then? Okay, we can probably forget that then. The name, we can read in the symbol or ignore it. We can change this if we want to and make it simpler. The half-life of the element, and an initial mass. Then after so many years, h divided by, y divided by h, all raised to the 1/2 times the initial mass, we would have a decay table that looks something like this. Initially, we'll have 10 grams, or I guess in this case, or kilograms, whatever you want. After 1 year, it is decayed to 9.76 kilograms, or grams. After 2 years, it is decayed to 9.53. After 29 years, we're now down below that original 1/2 of 10 kilograms, or 10 grams, right? And that's the table that I want to produce, right? I want to see how it decays during that first half-life epoch, right? Okay. So let's go ahead and create a new, this is a refresher, right? New, since if you were using the same project all throughout last semester, probably haven't created any new projects since then. New project, Java project. You could have selected it directly there, right? And I'll call this assignment -1, 00, whatever, for H, right? Doesn't matter what Java you select, as long as it works in the grader. That's a good question. What is the grader? Ooh. Let's ask. SSH into Neuros. That's the server where the grader's on. Java version looks like it is 21. So do not go with 22 or 23. Right? Go with 21. Right? Javac version 21. Go with 21. Right? So go with 21 for all of your projects. Make sure that you have disabled this. The first time you disable this, the first time you look at this, it'll be enabled. Once you disable it, any new project that you create will be disabled. This is the module info file that'll just get you into trouble later on if you have that there. So make sure you've disabled that. Finish that. So you've got a source file there, right? If you want to, you can. You should create packages, unl.soc, right? I'm just doing unl.soc because that's who we are, right? For your actual project, you would want to name it like com because of commercial. This is UNL, edu or something, whatever you want, right? Whatever makes sense, right? And then create a new class here, which I'll call isotope demo. Right? We want a public static void main string args. Right, there we go. And now we're going to read in that those pieces of data. We'll simplify it immediately here. I don't know what the atomic number is. I don't want to look it up. Let's just, what is it?
The big number.
Is it 90?
No, it would be 28. I heard 38.
Where is it? Where did I write that?
On the table you made.
Oh, it's in the table. Okay, 38. There we go.
And it says above. So
Okay. Screw it. Name, half-life, and mass. That's all I want. Right? So, name is going to be a string. Half-life would be double half-life. Right? And double, we'll call it initial mass. Right? Okay. Because eventually it's going to go down. We're going to change that. And I do want an initial mass to keep track of what the original mass was. Right? Okay, again, we're doing this imperative. We're doing this like you would do in CS1 with the way we presented Java. We're not doing it object-oriented yet. We will do that later. But I would, of course, check for command line arguments. If args.length, args.length is not equal to 3, then I'm going to issue an error message using the standard error. Printf usage would be name, half-life, and initial mass. Right? End the line, and that's it, right? And there's no way to recover from this, so I'm just going to quit on them. System.exit 1. Now, if I just run this, of course, usage, I need to provide a name, half-life, and initial mass. Remember how we do this in Eclipse through run configurations? Right? Over in Strawn TM90, what was the half-life? 28.9 years, let's say, and then 10 kilograms to start out with. Apply that and run it. Right? No news is good news because we haven't written anything yet. Okay. By the way, is anybody not using Eclipse? Is anybody using VS Code or IntelliJ or VS Code? When you go to build, if you want to, go ahead and write up how to build so that it works in the grader. This is for the project because you need to build a jar for the project. And help anybody else that's in VS Code. If you're using IntelliJ, I do have a handout for that if you want to use IntelliJ and generate a jar file. But I don't have one for VS Code. Right. This is going to be args of 0 because there's no conversion from a string. It's already a string. This is going to be double.parse double because I need a double out of that. And this also is going to be a parse double, but it's the third command line argument. There we go. All right. Let's go ahead and generate this thing right here that looks like this. Actually, I'm going to select all that. Right. That's kind of like my header. String header equals. Do we remember the 3 quotes? It allows me to do multi-line strings. And then I'm going to go through and replace these with the name. We agreed not to do that, so I'll get rid of that entirely. And then I'll say system.out.printf header with my name. If we want to, we can add other stuff with half-life is going to be equal to %.2f, right? And then we can put that in there as well, half-life. Right? Oops, what?
Put half-life in your system.
Thank you. Order is important, isn't it? There. So it looks like something like that so far, right? All right. Obviously, this is going to be a loop. What kind of a loop do we want to use? A while loop. You could use a for loop if you really wanted to. But I'm going to use a while loop here because I don't know up front how many years it's going to take me to get down below. I do technically because that's what the half-life is. It's just going to be the next integer above that. Right? So, while the current mass is greater than or equal to the initial mass times 0.5, in other words, half of the original. And so I need this variable here. Let's put that up here. What should I set that equal to initially? Yeah, the initial mass, right? I could set it equal to 0, but where do I want to start? I want to start out at that 10 grams or 10 kilograms or whatever, right? Okay. All right, so while that, I will say system.out.println, or printf, because we want to look pretty. %d, that's the year, right? Elapsed years. And then the amount there, so that's going to be %2f, end the line. So I need a year, the current year, and the current mass. All right. All right. I don't have a year. So let's go ahead and create that. And that will be an integer for now. What should I initialize that to? 0? Okay. 0. All right. And As you go along, what should you do to year? Plus plus. Now, if I were to run this right now, predict what's going to happen?
You're gonna get instantly.
Yeah, why? Because I'm not changing that mass. It's 10 kilograms, 10 grams, whatever it is. So remember how to kill this? Stop button. You can clear it out as well. So we need to change the current mass. Current mass is equal to the current mass times 0.5 raised to the year divided by half-life. That was the this right here. The current mass times 1/2 year by half-life. I can't do that. But in Python, we learned we can do that natively. How? Star, star. Can't do that in Java or C. Instead, you need math.pow. Right. Careful on this one.
You should update here before you
Okay. Yeah,
comes out 0.
let's find out. Let's run it. Okay, so 10, 10. Ah, okay.
We print out the year first.
Okay.
I guess we could theoretically print out a year before the while loop
All right.
as well.
In fact, what we system.out.println, printf, right? That first year is different than all the others, right?
Yeah.
That's no year. And that's the initial mass. So, no year, and then initial mass. Right. Okay? And then we can say year plus plus, because we started it out at 0 up here, so I'd go immediately plus plus, or I could start it out at 1. Right? There we go. And then I could update it down here, year plus plus. You just have to be careful on where you start and where you end up. Let's see if that worked.
Even with current mass.
Yeah. So, actually that's correct, right? So far. 8 years?
And it doesn't go below half mass.
Yeah, it doesn't go below, well, it does technically, but we're off. We're off anyway, right? We're off because it doesn't take 8 years to get down to about half. The half-life was what? 28.9. Right? So each iteration of this is what? 1 year. Right? But I'm going 1 year, then 2 years, then 3 years, then 4 years. Right? So in that 4th year, I'm decaying it 4 years in 1 year. Change that to 1. Right? And 1.0 to be safe. It's not safe. You don't need to be safe because this is a double already. But there we go. All right, that's looking nice. 1 year, 10. I could skip that basically, right? But we're off by 1, right? Now I do need to move the year up there, right?
No, you need to move current mass before you bring.
Okay, we could do that too. And I'd restore that. Year plus plus. There. And we're starting out at 1, so that should be okay. There we go. That's looking more like this, 9.7. Then we get down to 4.99 in year 29. All right, that looks right. We did it. But the point here is, what? Do we have any objects here? No. Do we have the concept of an object? Yeah, what? An isotope. An isotope has a name, a half-life, and a current mass, or and a mass. Well, I'll just say mass. I don't want to call it initial or current yet. Okay? So let's go up here and create an object to represent that thing. Isotope. That's why I called it isotope demo. And I'm going to take these 3 things and I'm going to move them over there. Not exactly, but let's go ahead and get rid of that. Get rid of that. I'm going to change this so that it's mass. Right. There we go. Oh, and then the name, sorry. String name. All right. Okay. So do we remember encapsulation? We'll start forming notes next time, but encapsulation is actually 3 things. It's the grouping of data into one logical unit. That's what I've got right now. I'm taking 3 pieces of data and I'm grouping them into one class. It's the protection of data. Am I protecting this data right now? No. Let's make it into what? Private. You remember those tricks? Option Command A to go into block selection mode. Right. Okay. Now I've protected that data. Then the third thing is the grouping of operations that act on that data. We're going to get there here in a second. Before we do that, though, let's do the boilerplate stuff. What do we need to do to be able to create an object? And that's called a constructor, right? So let's go ahead and create a constructor. Nice. Right. Let's go ahead and create getters and setters, because remember, CRUD also CRUD, create, retrieve, update, and destroy. That also applies to objects. I've got a way to create an object here, but do I have a way to retrieve its stuff? Nope. So let's go ahead and generate getters and setters. I'm going to go ahead and do them all for a second. Right. There we go. Oh, didn't I do them all? Okay, there's the getters. So that's the retrieve, right? The update. You can go ahead and do setters. Let me go ahead and show you what they look like. Get setters. There we go. All right. Set name, set mass, set half-life. Is Strontium 90 going to change its half-life? No, not unless the fundamental laws of the universe change, right? So should I allow somebody to just go ahead and set whatever they want? No. Right. Now I've got the protection of data. Create, retrieve, update, destroy. Do we have a destroy in Java? That's a good question. No, because of memory management. Right? If you create an object and then you no longer need it, you don't call free to free it up. Right? Here's an aside though. There is this thing called system.gc. What do you think GC is short for? Garbage collection. Right? This is a way that you can suggest to the garbage collector that it do its job. Right? There's no guarantee of it though. What the garbage collector will do, and there are various algorithms for this, the garbage collector will say, yeah, it's worth it. It's worth it to reclaim that memory. Or it'll say, there's so little memory that's not being used, I'm not even going to bother cleaning it up. Right? And there are very good algorithms to do that. In fact, you can run Java with an algorithm and then an alternative algorithm. You can write your own algorithms for garbage collection, right? You can monitor that garbage collection. You did that in Lab 7 last semester. If you did the Java version, we set it up so that you could monitor the garbage collector, and it would output every few seconds, cleaning up 50 megabytes of memory, cleaning up 40 megabytes of memory, right? But it's automatic. Don't worry about it. If you didn't do a Lab 7, then go ahead and do it in a LARF, right? There we go. From last semester, the Java version from last semester. Right? I'm also going to add in something that's going to be, I don't know, we don't need it in this case, but let's go ahead and just do it like this, right? Isotope, maybe I want it to look something like this instead though, right? So string.format, the name, and then the half-life, %2f, and then the mass, %2f, kilograms, we'll say. Right. Kilograms will be our standard unit of, and I was about to say weight, but weight would be wrong. Why?
That's
Yeah.
force of gravity.
Yeah, weight is mass in the presence of gravity, right? So this dot name, this dot half-life. See, physics is cool and fun. This dot mass. Right? Anybody doing a physics minor? Just taking calc-based physics?
I take enough physics, I'm just
On what?
kidding. I take enough physics, I might just get one.
Oh, okay. All right. For fun. All right. So now that we've got this object, we don't have to separate these three things out anymore. What I'm going to do is I'm going to create an isotope. Right? Isotope. And I'm going to call it, I don't know, ISO. Right? I is kind of bad because that's an index variable. Isotope. You'll see that that's very common actually, just to name it the same class, but with a lowercase I. This is why we use upper camel casing. The upper camel casing, you know that it is a class. The lower camel casing, you know that it is a variable. Right? You isotope with the, what were the order again? Name, half-life, and mass. Was it that order? Oh, you're right. Mass and then half-life. That makes sense. Mass, half-life. There. Okay. All right, so how does this code change as a result of that? All right. In fact, if I were to throw these variables away, how could I do that syntactically? I could go ahead and do this and put that up there and then say isotope is equal to new. There we go. There. Now I've created a world in which you don't have those variables anymore. Right? Why? Because what I did is I put them into a different scope here. Right? You can have opening, closing curly brackets not bound to a loop, not bound to an if statement. It's just it creates its own scope here. Right? And because isotope is out of that scope, we do have isotope down here. So you might think, well, okay, isotope dot get name, right? And isotope dot get half-life. Right? That's one way of doing it, but all you're doing is, why did you create the object to begin with if you're just going to rip it open and pull its guts out so that you can dump them to the standard output? So what I'm going to do is I'm going to change this so that the entire object is responsible for itself, right? Isotope. We already wrote a toString method, right? What was the purpose of writing that toString method if we're just going to ignore it? Use it, right? And let me get rid of the rest of this stuff for now so that it compiles and I'll show you that it still works, right?
You change the mass.
Oh. Darn it. It's initial mass. There we go. Oh, and then I need this down here. I will give you that, right? Thank you. Initial mass, there we go. And then I can move this down to current mass. Nope. I need to declare it up here. I would not normally do something like this, but I'm trying to demo something here. So current mass is equal to that. I can move that back up here and get rid of that declaration. There we go. Now we're all fine. All right. And now I can run it and show you that who is responsible for formatting the string of the object? The object, right? Isotope stuff belongs in the isotope class. Book stuff belongs in the book class. Person stuff belongs in the person class. An isotope thing is to output it itself as a string. It acts on its own data, right? This dot name, this dot half-life, this dot mass. Let it be responsible. The one that we had before is I ripped open the object and then pulled out its guts, right? And then dumped them myself. What's the point of creating an object if you're not going to use that object, if the object is not responsible for itself? So that's the first way in which it changes. That's fine. That's not initial mass. What is it called? Current mass. Whatever. That's just the loop. Okay. Now let's go ahead and restore all of this. All right. What I'm doing is okay. So this is kind of weird because I'm actually changing the mass of the isotope. Remember before we protected our data by making everything private? And we made it so that you can't change the mass. Well, now I have potentially a use case for changing that mass. Let me go ahead and, just for mass, because half-life doesn't change, the name doesn't change. We're not renaming it. But just for the mass, let's go ahead and generate the setter for it. So expand all this mass, and then the setter. Just that one, right there. And now you can mutate, you can change, you can set the mass here. All right. Let's see what how that works. All right. And dude, now I do want an initial mass. Dang it, double initial mass. All right, and then I'll get rid of that there. Yeah, go ahead.
If it was in the scope, how is it printing out the...
Isotope was in scope because I declared it before, but I initialized it inside that scope. Right. Yep. All right, so while the current mass is greater than the initial mass times 0.5, right, the current mass is going to be equal to the current mass divided by the half-life. And so I'd say isotope.get half-life. Right, there we go. And I would need to change the mass of the object now. So isotope.set mass to be the current mass. Right. Okay. Let's see if that works. And then actually I'm going to change this as well to isotope.getMass. There we go. that we'll see that it's actually changing. And maybe the current mass, here what we could do is change that to the current mass as well, although it's not necessary. I think we're going to get the same thing here. Right? So, same output, 9.76, and then all the way down to year 29, 4.99. But a different philosophy. Right? Now we're using the object to do stuff. Right? But it's still not fully object-oriented programming. I'm still ripping the guts out. I'm ripping the guts out to get the half-life. I'm ripping the guts out to get the mass, so I can do this computation outside the class itself in this isotope demo class in order to just then put it back, stuff it back into the object. Is there a better way? Is there a way that the isotope could be responsible for all that? Yeah. What is it actually doing when it's half-lifing? It's decaying. Right? So public void decay. Right? That is, that is a mutator function now. Right? It's something that's going to change this object. Note that I got rid of the setter, right? Because I don't want you to just set it to an arbitrary value. I want you to decay. Decay by how much? How much? Right. Yeah, okay. So years? Right? Because maybe I want to decay it 2 years. Maybe I want to decay it 4 years. Maybe I want to decay it 1.5 years. Right? So let's document that. The rest of this crap, that doesn't need documentation except for the class itself represents a radioactive isotope. Right, there we go. All right. And this will, like the getters, the setters, the toString method, those don't write documentation for that stuff. All right. It's self-documenting code because what does it do? It gets you the name, right? What does that do? It gets you the string, right? So don't document that crap, right? Do document this because it does something different, right? So decays this isotope, that is, reduces its mass by the given number of years. Right? How do I know that it's years? Because that's what I named the variable, right? That's what I put in my documentation. What if I just said X? That's bad because what is X, right? So it's still bad this way though, right? Because what if I said, I didn't bother reading the documentation. I didn't bother reading the variable name. I said, I want to decay it by 5 months. I'll pass in 5. Right? I'm going to get the wrong result, right? But that's on me. I should have read the documentation. But is there a better way? Keep that in the back of your minds for now. For now, though, let's go ahead and take this behavior, is what it's called, right? This is data, state. This is behavior, functions, functionality. Right? So I'm going to say, not this me, this dot mass, right? Oh, this dot mass, times that times this dot half-life. I don't need to call the getters, by the way, because I'm already in the class. Right? And it knows me, myself, and I, this. Right? And I can say that this mass is now equal to that. And I don't need to call the setter because it's not even there anymore. Right? There. Did it? No, sorry. That should be years. Years divided by. There we go. If it was 1, then of course it would decay by 1. Now, how do we do this over here? Right? Let me replace all that. I'm going to call the isotope dot decay by 1 year. Right? And then I can get its mass after that 1 year. Let's run it again, see if we broke anything. Oh, we did break it, something. Darn it. Say what?
I just know that doesn't matter.
Here, instead of
Oh, sorry, current mass. We're not changing current mass. What is it? Isotope dot get mass. There. There. Now we get down to, there we go. All right. How much cleaner is that? Decay. Right? Decay yourself by 1 year. Why do we like that? Math dot square root 2. the question I usually ask when we talk about the math library is, or when we get to functions, is how does that work? It just does. Who cares, right? If you really want to see, there's strict math, and strict math then becomes compute. There we go. Yeah,
Yeah, it just does.
it just does, exactly.
Even,
What is it doing? Well, it's shifting by one, right? These are all probably just cases, right? If. Wow, that's complex, right? Some really smart people figured out what that compute should do, right? And by the way, it's complex because there are IEEE 754 rules on what should happen with floating point numbers, and so it's capturing all those rules. Spoiler alert, you're probably going to have to do something like that in 230 or 231. Right? You're going to have to write that stuff. Right?
What is your target?
To computer architecture. Right. All right, but now object-oriented programming. How does it decay itself? Who cares? Right? Now, you care if you actually have to write the function. Right? But here's another example that we've already looked at. Local date time. Well, actually, let's just go with local date. Today equals local date dot now. Right? Wow, that's cool. How does it represent a local date? An ISO 8601 string? A Unix epoch number long? Or 3 numbers? Right? Again, what's the answer? Who cares? Right? Because we have what's called abstraction. Right? We've abstracted away the details so that you don't have to worry about it. Just decay yourself 1 year, decay yourself, right? Don't anthropomorphize isotopes, right? So, much, much simpler. Now, in the last 5 minutes here, I want to come back over here and ask the question again. Years. What if I wanted to do it by days instead? Yeah, let's try it. Decay by days instead. Now, what would I do over here? It would be days divided by 365.25, right? Days. And then I would, of course, update the documentation.
Can you make it use days?
Okay.
Does that fix the overload problem?
Well, what if you want it a day and a half? That'll fix the overload problem, but yeah, tough luck. Okay. Right. I want both. So decay years, decay days. Right. What if I gave you something completely different? A duration? Another object-oriented programming. Duration. Right? A duration that can represent whatever you want. Right?
we need a
Or
better-
it's actually probably better, period. Right? A period of time. Period of time. Right? We don't need to because it's already built into the Java time library. Right? Now, unfortunately, we do need to do some math because for the life of me, I could not find their justification for. There is a duration and there's a period. A duration is usually used for less than a day. A period is used for more than a day. But still, there's no way to get like the number of years out of it. Period dot get years. If it's 1 year, 5 months, and 3 days, it'll still only give you 1. Right? So int years, right, is equal to that. Int months is equal to period dot get months. And int days is equal to period dot get days. Why are they all integers? Don't ask me. I don't think that's a very good design. Because how many days are in a month? Yeah, it depends, right? How many days are in a year? Depends, right? But unfortunately, there's no good way to I just want the total number of days. Int total days is equal to period dot days. There is no way to get that, right? Unfortunately. So what we have to do is we have to estimate the math, right? What is the total number of days? And I'm going to change that to a double, right? That's going to be years times 365.25 plus months 30. Actually, the average is going to be 365.25 divided by 12 times months That's the average number of days in a month, by the way.
Yeah, months.
Oops, sorry, plus, okay, get rid of the months first then, plus days. Now, that's still not all that satisfying because, like I said, period is used for more than a day. There's no way to get seconds or hours out of that. So maybe the answer is creating your own custom duration or period, right? But I don't want to go that far. So instead, I'm going to go total days divided by 365.25. There we go. And that's a good estimate. Right? So that over here, now decay is not taking one what? Right? There's a paper that I was reviewing the other day, and they said that they were saying that students are given 5, period. Like, five what? Right? So basic error like that, it was not a good review. Right? Anyway, we need a duration, or period, right? Period year is equal to, I don't know, a period dot of. You can give years, months, and days. So 1, 0, and 0. There's a year that I will decay it. A year. There we go. Right. Now, do you have to worry about what the period is? That it's a day or a year or whatever? Right? Nope. Given period. Right. There we go. And period there. And better than that, you can actually link to this. What would it be? At link period. There. That's in the Java time library. And so if I hover over this, I can go ahead and take a look at the period. Right? It'll take me to the documentation for that. Right? A lot of concepts, a lot of principles that we've just talked about that we're going to formalize on Friday. Stuff that is isotope related, where does it belong? In the isotope class. Stuff that is not isotope related, it belongs in a different class. For example, duration. When you're designing your objects, break it down into the constituent parts until you have something that represents it for you. Right? How does it represent it? Who cares? It just does. Right? How does it do? Okay, 3 numbers, years, months, and days. That's why it's limited to that stuff. But in any case, and then we had to do our own math, unfortunately.
Does documentation tell you how many days are in a month?
There is no concept of that in this. How does what?
Does it, like, if you were to give it,
Do you pass it 88 months or something?
yeah.
88 months? Yeah, I think so. Let's try it. Instead of 1 year, let's go with 13 months. It'll work. Yeah. It'll interpret it as 13 months. Right? 0 years, 13 months. It doesn't overflow into the other one.
So
So it
you
doesn't.
could have like a year, 13 months, and
Well, it's not a year. It is a duration of a year of 13 months, right?
So it doesn't take the 13 and be like, oh, that's a year. And 1
Nope.
month.
In fact, when I output it, it looks like this. There? Yeah, 13 months. Oh no, it
no, that's the one from the
months.
year, that like when the writer.
For one we're printing out.
Oh, thank you. There we go. The period is 13 months. Right? If I gave it 1 year and 13 months, it would say 1 year and 13 months. Right? There. 1 year, 13 months. Yeah, but it's much better than now. That's a different concept. The duration, period, and I don't want to say period again because it's not, but it's a start date and an end date, right? You can think of that as a period, but it's a duration. So once you start attaching like specific starting points to it, then it becomes a date time thing, right?
If you wanted to just have it, like, take the period and just say,
Yeah, well, it would be local date, like local date dot between, date time dot between. That's something like that. I forget what it is. And then you have date 1 and date 2.
yeah, but like if you wanted, if you said like 13 months, but then it would just automatically, like,
Yeah, well, if you said today plus 13 months, plus this period, yes, it would go 13 months into the future. And it would give that to you, right? So period, duration, there's local date time, right? And there's no perfect design because, the real world has things like leap years, leap seconds, as by the way, too, because of the rotation of the galaxy and our solar system and stuff like that. So there is no perfect notion of time. And then we've got the daylight savings time, which ends soon, I think. I'm not sure.
Nebraska like getting rid of it.
Well, the federal government was supposed to get rid of it, but they can't do anything. So, yeah, there was a bill there to do it, but it never passed. I think it passed the House, but not the Senate. So, unfortunately, we're still stuck with it.